Good evening, viewers of Optical by Vetri from Pondicherry. Today, I am going to discuss another most important basic concept in organic chemistry is isomerism. And we have discussed under the classification, that is, the organic compound can be differentiated from inorganic compound. Mainly the most important factor is isomerism, because generally organic compounds will show isomerism, whereas inorganic compounds will not show isomerism except coordinating compounds. This I have discussed under the classifications. So today, let me continue. I will discuss what is isomerism, what are the types of isomerism possible, competitive point of view. Optical, that is, coming for the optical isomerisms. So this is coming under the, I have already discussed you. That is, isomerism can be broadly classified into two types. One is structural, another is stereo. Structural we can further classify into four types: chain isomerism, positional isomerism, functional group isomerism, and metamerism. So that I have just now I have discussed in the previous lecture. Now, what is the next one? That is, another type is stereoisomerism. The stereoisomerism we can further classify into optical and geometrical. Okay, so today I am now going to discuss now in this lecture what is optical isomerism, what are the compounds which show optical isomerism, what is the way we have to discuss suitable examples. So before that, let me discuss, that is, what is stereoisomerism, then I will go for the optical. What is stereoisomerism? Let me define now. Compounds having same molecular formula but difference in spatial arrangement of atoms or groups around central atom. Kindly remember, around the central atom or atoms are called stereoisomers, and the phenomenon exhibited by this stereoisomer is called stereoisomerism. Let me repeat again. Compounds having same molecular formula but the difference in spatial arrangement of atoms or groups around central atom. Around central atom indicates it's an optical isomerism, or atoms it indicates it is a geometrical isomerism. So the definition itself is very clearly given. Groups, the difference in spatial arrangement around central atom means optical, around more than atom means it is two different means, we'll think of geometrical. So they are called stereoisomers, and the phenomenon exhibited by this stereoisomer is called stereoisomerism. Okay, let me give you a specific example and we'll discuss. So, the stereoisomerism, as usual, I can classify into two types. One is optical, another is geometrical isomerisms. So today, I am going to concentrate optical isomerism in this class. Okay, what is optical isomerism? Specific example, definition of the you know. As usual, let me go for the definition of optical. Compounds having same molecular formula. You can come across always in all of the isomerism, first sentence start with always this is the sentence. Compounds having same molecular formula. It is, we are repeating the same thing, same sentence. Compounds having the same molecular formula but difference in optical activity. Difference in optical activity are called optical isomers, and the phenomenon exhibited by these optical isomers is called optical isomerism. So let me repeat again. Compounds having same molecular formula but difference in optical activity are called optical isomers, and the phenomenon exhibited by this optical isomer is called optical isomerism. Molecular formula should be same, but optical activity will be different. Next question arises, what is the optical activity? How to understand this? Let me explain. What is optical activity? With a suitable example, then you can understand. So for that, let me explain. Specific example I will give as usual for optical isomerism. So optical isomerism, specific example, I will take now lactic acid. It is already given in all our books, textbooks. Either CBSE or Samajit, this is the commonly given book. Lactic acid, it is present always in milk. The molecular formula, that is C3H6O3. This is the structural formula C3CHOX COOH. This is the structural formula. Molecular formula C3H6O3. Okay. Now, the same compound, molecular formula is same, C3H6O3, but with the help of a polarimeter instrument, if you measures optical activity, I will come later what is optical activity. If you measures optical activity, one will give you a positive value, other will give you a negative value. That is plus we are indicating. One is D lactic acid, another is L lactic acid. Kindly students, small d indicating plus. It's called textorotatory. Small L or minus indicate a levorotatory. So let me explain now. What is textorotatory, what is levorotatory, what is optical activity, I will explain. But for this specific example, optical isomerism, lactic acid is a specific example. It exists in two forms. One is rotating plane polarized light clockwise direction, another is rotating anti-clockwise direction. Okay, all this information I will show now. I will explain now. Now, just see. What is optical activity? This is the definition. When a plane polarized light, I will explain what is plane polarized light. When a plane polarized light is passed through a solution of a sample in a polarimeter, in the instrument we have to take a solution and we have to pass a plane polarized light. Okay. Depending upon the nature of compound, the compound will rotate the plane polarized light either clockwise or anti-clockwise direction. It can rotate clockwise right side or it can rotate anti-clockwise left side. It will rotate. When a plane polarized light is passed through the solution of sample in a polarimeter. Okay. If it rotates, the light is getting rotated clockwise direction, then it is called textorotatory. If it rotates clockwise, we'll call it as textorotatory, usually represented by small d or plus. Small d or plus. Don't write capital D indicates configuration. And if it rotates anti-clockwise left side, it is called a levorotatory, usually represented by L or small l or minus. This is too important information. So we have to pass a plane polarized light through a solution of sample in polarimeter. If it is getting rotated clockwise, we'll call it a textorotatory. Usually we'll represent by small d or plus. If it rotates anti-clockwise direction, we'll call it as small l or minus. Okay, let me explain that fact also. Now you can see the explanation now. So this is ordinary light. What I am showing here is ordinary light. You know already, ordinary light vibrates in all directions. Very simple. Ordinary light vibrates in all directions. When this ordinary light, it is passed through a Nicol prism. So all the radiation is coming and hitting the Nicol prism. The Nicol prism cut off all directions except only one direction, which is perpendicular to the line of propagation. This is the line of propagation. So it is allowing only one light which is perpendicular to the line of propagation. That light is called plane polarized light. I hope now you can clearly understand. When ordinary light is passed through a Nicol prism cut off all direction except one direction which is perpendicular to the line of propagation. That light is called plane polarized light. When this light is passed through a solution that is present in a polarimeter, now it can be rotated either clockwise or anti-clockwise. That can be measured with the polarimeter. So this is the original position. This is the original position. O indicates original. So what will happen now? From this position, it is rotated clockwise. So the angle we can measure. It is the angle of rotation we can measure with the help of polarimeter. Its value will come plus value. Plus 1, plus 2, plus 3, it will go any number. The same way, this will be usually, if the plane polarized is getting rotated clockwise, we will call it as textorotatory, that is small d or plus. This is the experimentally measured quantity. Otherwise, some cases, this is the original and it can rotate from anti-clockwise direction. In that case, now we will call it as a levorotatory or usually represented by small l or minus. So whenever in chemistry we are representing within bracket small l or minus levorotatory, small d or plus means textorotatory. You should not confuse with capital D or capital L. They are indicating configuration. I am repeating many times, kindly have it in mind. Okay, let me go for the next. Now, optical isomerism. So I have already defined what is optical activity. I have defined now. So optical activity, it is the experimentally measured quantity we can measure with the help of an instrument called polarimeter. We can measure positive as well as negative values. Okay. Now, what is the condition to show optical activity? Now, normally when you are going for any examinations, so question can be, if question is one among the following things having optical activity will show optical activity, one among the following example will not show optical, all these questions will show. Now let me explain how to answer for this question. So to be optical active, what is the condition? A molecule should produce a non-superimposable mirror image. Very, very most important condition. Suppose you want to say this particular compound is show optical activity. Now, if you want to prove, what you have to show that you should, whether the molecule produces a non-superimposable mirror image or not. If it is producing a non-superimposable mirror image, it will optical active. It is not, then it will not show optical activity. So, specific example here. This is the image left side. Call it as is an image. You take a mirror, construct a model again. This is a mirror image. So, you take that image, construct a mirror image and fix one over the other. If it is fixing one over the other, that is called superimposable. If it is not fixing, it is called non-superimposable. So, you must have the difference between what is superimposable, what is non-superimposable. So, specific example, so kindly listen me. You can see here, this is the model for the methane. This is the model used in all European universities. Okay, now the center here it is carbon, black one, that is carbon, and this white is hydrogen. This is a tetrahedron. So 4 hydrogens are there, center is carbon. Now what will happen now? In this case, suppose this is the imagine this is a image. So I am putting a mirror image. If you put a mirror in between, so it's a mirror image. So this is the original, this is mirror image. So after construct, if you take this mirror image and I am trying to fix one over the other, when I am trying to fix one over the other, it is fixing superimposable. So methane is producing a superimposable mirror image. So methane is not optically active. Very, very simple. So any molecule which produces superimposable will not be optically active. A specific example I am giving here. Okay, now let me go for the next one. Suppose you can see here a non-superimposable mirror image. In this case, you can see now that is my left side and right side, the 2 fingers which is given. The one, let us assume this is the original image, this is the mirror image. Now, if you just construct, if you fix one over the other, they will not coincide. They will call it as non-superimposable mirror image. So now you can see, suppose this is my finger, left. I am showing my left finger in front of you. So mirror, this is the original image. So now I am putting a mirror image. This is a mirror image. So if I am able to construct and if I am able to bring out and fix one over the other, which will not be superimposable. What you are seeing in the screen now I am showing you. So it is non-superimposable mirror image. This is a specific example you can see here. So these two, one over the other if you fix, it is not superimposable. So it is non-superimposable mirror image. So what is the information here? To show optical activity, any molecule produces superimposable will not show optical activity. Any molecule which produces non-superimposable mirror image will produce optical activity. This is the base. Okay, let me now explain with the example. Now just now I have shown you model methane. So methane, I have already shown model. This is the methane, you are seeing this. So this is the methane. And the right side, this is the mirror image. So I have already explained you, if the mirror image, if you try to fix over the image, then it is exactly coincide. It is superimposable. But in this case, I am giving a lactic acid. So now in this case, methane is superimposable. The lactic acid is not superimposable. I will show you now model. Now see here. So in this case, what we are seeing is lactic acid. So lactic acid formula we know already. That is CH3, CHOH, COOH. This is the formula, molecular formula for lactic acid. Left side I am using now D minus lactic acid. Right side I am indicating L plus lactic acid. So students, kindly have it in mind. So capital D, it is configuration. I will be discussing in a separate lecture class. Capital L, again configuration, indicating. So timing, let me give us an idea. That means in asymmetric arc, that is, we will be discussing that any Optically, that is the more electronegative atom or group on present on the right hand side, will use always D. Any electronegative or atom or group it is placed in the left side, we will call it as L, capital L. I will come back later. So the minus and plus indicate, I have already explained you, it is the measured quantity, optical activity. In this case, now I am showing now. So the lactic acid, it is now producing the mirror image, and mirror image, if you try to fix one over the other, it is non-superimposable. So if you are able to take this mirror image by concept model and try to fix one over the other, it is not fixing. So these two examples, D minus lactic acid and L plus lactic acids are non-superimposable mirror image. Non-superimposable mirror image. So just see here, this is the model I have with me. So now, so D minus lactic acid, I can show you now. This is the lactic acid. D minus lactic acid. So if you want, I can show you the another dimension I am showing now. So what I am having here is center is carbon. This is hydrogen, CH, and this is O. The red one is O, again H. So CH-OH, and this side, this is CH3, methyl group, carbon, H, methyl group, and this one, carbon, CO, double bond, and this is OH. So all the groups, this is the actual model followed in all European university. Let me repeat again. Center is carbon, here it is H, now here, this is the red one, left side it is O, this is H, OH. OH, right side CO, OH, carboxylic acid groups, and bottom, you can see here CH3. So CH3, H, COH, COOH, sorry, that is CH3, H, OH, COOH. This is the lactic acid. So when I am now keeping this one, so when I am keeping this, you can see here. Now you can view from you. Now I am keeping in front of you. So if you view this, for your right side OH group, that you can see in this model. The left side model is the board, the model that you are seeing. You know, on your right side OH group, on your left side is H, and this is CH3 bottom, and above is COH. Okay. Now this is D minus lactic acid. The same, but now what I am showing here is again a mirror image I am going to construct. Just see here. This is the mirror image. So what you are saying, on your right side is the original mirror image. This is the mirror image. Just see exactly it is coinciding. So this is my left hand, but according to you it is on your right. This is D minus lactic acid. This is L plus lactic acid. Exactly mirror image. So if you try to fix one over the other, automatically just think of here it is not fixing. This side OH, H. OH, H, but the other two, if you go there, other side, it is CH3 fixing, COOH, it is fixing. That means when I try to fix L plus lactic acid over the D minus lactic acid, automatically they are non-superimposable. Because with the board, if I say construct and keep it one over the other, I am showing with the model. So I am already have two acids. One is D minus, another is L plus lactic acid. When I try to fix one over the other, only two groups are coinciding, other two it is not coinciding. H and OH is different. So this is the most important information. So the D minus lactic acid and L plus lactic acids are non-superimposable mirror image to produce. But unfortunately, when you go for any examinations, so we are not allowed to carry the model, and we cannot even predict, and we can see all this information. So there should be some short route to identify to whether it's a particular compound is optically active or not. Okay, let me explain this factor now. Okay. What are the conditions to show optical activity? This is the experimental pattern. When you go for a classroom, when you go for examinations, when you go for interview, so immediately you have to answer whether the particular organic compound is optically active or not. So for that, what we have to analyze? What are the conditions we have to analyze? So I have given 4 conditions. To produce a non-superimposable mirror image, your molecule should have 1. No plane of symmetry. 2. No center of symmetry. 3. No axis of symmetry. And finally, no alternate axis of symmetry. So, to produce a non-superimposed mirror image, only if any molecule produces non-superimposed mirror image, it will be optically active. So I can say now, to be optically active, a molecule should have no plane of symmetry, no center of symmetry, no axis of symmetry, and no alternate axis of symmetry. Even though I have given 4 points here, your level, your higher secondary level, the first one is sufficient. Plane of symmetry will be sufficient. But on the remaining will be some higher level. Anyhow, I will just point out, indicate for informations, but I will concentrate only on plane of symmetry. What is the plane of symmetry? What are the types of plane of symmetry? What is center of symmetry? What is axis of symmetry? What is alternate axis of symmetry? Let me explain now. Because only if you understand, you can easily answer for any competitive questions regarding optical activity. Okay, let me come for plane of symmetry. So plane of symmetry is usually indicated by sigma. What is a plane? A plane of symmetry is one which bisects a molecule into two equal halves. Any plane which bisects a molecule into two equal halves, so that one half will be the mirror image of the other. Let me repeat again. A plane of symmetry is one which bisects a molecule into two equal halves, so that one half will be the mirror image of the other. Now see here, example here in the board. So a round circle is given, the plane is indicated. I am calling this is a plane of symmetry because this sigma indicating, because it is bisecting into two equal halves. One half will be the mirror image. So any plane which bisects a molecule into two equal halves, so that one half will be the mirror image, the other is called plane of symmetry. This will indicate with sigma. Okay. Now, so this plane of symmetry I can classify into three types. What are they? Number one, vertical plane of symmetry, horizontal plane of symmetry, and third, diagonal plane of symmetry. So when you say plane of symmetry, it means that's generally sigma, but we should be very carefully analyze. There are three types of plane of symmetry: vertical plane, horizontal plane, and diagonal plane of symmetry. So vertical plane is indicated by sigma v, horizontal plane of symmetry indicated by sigma h horizontal, and diagonal plane of symmetry is indicated by sigma d. So all these three planes I will explain with a suitable example by taking benzene. Now, so before that, let me take a specific example. Kindly listen me. What is, now you can ask a question. The plane of symmetry, we know we have written already methane. This is the methane for by Fisher projection. Normally it will be represented. Now one information I want to give, kindly listen me students. That is, board, notebook, everything two-dimensional. Two-dimensional. Whereas molecule what we are imagining is only three-dimensional. So normally we are representing a molecule, three-dimensional molecule in two-dimensional board. So if you are seeing this methane molecule, we are written in the two-dimensional. So but if you see that, but we have to imagine the form of three-dimensional. So what you are seeing is the molecular model for methane. So what is the plane of symmetry? Now just see, I am going to cut like this. When I cut like this vertical plane, that means I am cutting through this carbon black. It is dividing into two equal half. Even this carbon hydrogen bond, this carbon hydrogen bond will cut again, so into two equal half. So vertical plane. The methane is having a vertical plane, so it is not having plane, that is not optically active. It will not produce non-superimposed. So suppose another way, is it having a horizontal? Now let me explain. So it is not having any horizontal plane or diagonal. Let me go for that. The benzene I will explain. So why I am selecting benzene, because all the three planes of symmetry are present in the benzene ring. So this is vertical plane. Now let me show you now. So this is the benzene molecule. Kindly follow me. Benzene is a planar molecule. This is a benzene planar molecule. So what is the important information is, so alternatively single and double bond is present, benzene. So you know the structure of benzene is, this is the benzene, 1, 2, 3, 4, 5, 6. So between 1 and 2, let me see here in this case. So if you are going for according to your right, so now number 1 your right side, this is 1 and 2, single bond, then double bond, single, double, single, double. Alternatively, this is the benzene structure. So the important information is, suppose I want to cut this benzene. What were three? I have already informed you. All the 3 planes of symmetries are present in the benzene ring. So in the board I have already shown. Now I will show the model. Suppose I am cutting. That is, this is the vertical. This is the vertical plane. Now this is the vertical plane. It is cutting this hydrogen, carbon, again this carbon, this hydrogen. If I cut these 2 identical and these 2 identical. Okay. Suppose this is vertical plane. So usually indicated by sigma v. Suppose if I am cutting like this way, this is horizontal plane. So automatically these 2 are identical and these 2 are identical. This is called vertical plane. And third one is, this is the horizontal plane. This is the horizontal plane. This is the diagonal plane that is indicated by sigma d. So it is now in this case, these are the 2 are equal. Kindly follow me. These 2 are equal. Automatically the diagonal we are. So the same way here, these 2 are equal. So on the 3 planes, this is the model. I kindly see me now. That is single bond. That white indicates single bond, and the top and bottom here it is a double bond. It is indicating. So in benzene ring, it is a planar molecule, double bond, single bond, double bond, single bond, and double bond. So it is alternatively it is present. So this is hydrogen. So C6, H6. This is the structure of benzene molecule model. Okay, let me come back here. Now you can see here. So I have already shown this is the vertical plane. So automatically I can use these 2 terms. This side, let me use now the corresponding in ortho. They will call it as ortho. The left side, right side is ortho. And this is called correspondingly with this, any group is there. So this will be meta, this will be para, they will call it as, if any substitute is present. So these 2 are identical and these 2 are identical. So as per the vertical plane. The same way, if you go for horizontal plane, I have already shown you, these two are identical and these two are identical. As per this, again these 2 and these 2 are identical. So that means that is the plane again. So the third option is, this is the diagonal plane. I have already shown you. In that case, these 2 identical and these 2 again identical. So in benzene, all the 3 planes of symmetry, vertical plane, horizontal plane and diagonal planes are present, and this, because of 3, benzene is optically inactive because it is having a plane of symmetry. So to be optically active, molecule should not show the plane of symmetry. You should show no plane of symmetry. You should have no plane of symmetry. That is the most important information. Okay, let me explain for. I hope I have given a very clear idea what is the plane of symmetry. And there are 3 types: vertical, horizontal, and diagonal. I have already explained by taking specific example, benzene. Okay. Now, center of symmetry, I want to explain. You take carbon dioxide molecule. This is the structure of carbon dioxide. So let me explain how to define center of symmetry. You take any molecule. Molecule means more than one atom. Move from one atom toward the center. After moving the center, you move opposite direction, the same distance you have moved already. If the same atom or group is present, then we'll call it as the particular molecule is said to have center of symmetry. So in this case, now I am the carbon dioxide. I am moving from the oxygen towards left. In this case, carbon is their center. And again, if I move opposite direction, again oxygen is there. So both cases oxygen. So I can call it as carbon dioxide. Carbon is the center. So it is having a center of symmetry. But if you go for carbon monoxide, it is not having a center of symmetry. This is the center. So if I move center on opposite side, it is carbon. So CO is not having a center of symmetry. So this is the most important information. Another interesting information I want to give. We take methane. I have already pointed out. So question is asked. How to imagine, because it's a 3-dimensional model, whether a particular methane is having a center of symmetry or not. It is not having. Just see here. Suppose this is the model. So I am starting from the hydrogen, moving towards this carbon. Opposite side, if I move, nothing, no atom or group is present. That means methane is not having a center of symmetry. But if you see the model, that is, if you see the blackboard, 2-dimensional blackboard, then you will be getting confused. What is the information here it is? So, here if you start from the right hand side hydrogen, if you move towards the left side, it is having a hydrogen. Kindly remember, one that is possible only in two-dimensional methane. We are writing on the board, but really it is not real. It is only happening in the two-dimensional. In three-dimensional, you can imagine that I am starting from hydrogen, moving to the center. Opposite, there is nothing. So, as per the three-dimensional model, there is no center of symmetry for methane. Whereas, if you go for two-dimensional, then we are having a center of symmetry. So, the most important information is center of symmetry. We have to analyze very carefully, because we may do mistakes in the two-dimensional board or notebook compared to the three-dimensional. Always, when you go for examination, we are not allowed to carry the model, so it is not. That's what I am saying. Your level, plane of symmetry will be sufficient. We can solve all the problems. Even there are methods, I can give you a short rule to identify the optical activity. Okay. Now the next one is axis of symmetry, usually indicated by Cn. The center of symmetry is indicated by I. This is axis of symmetry will be indicated by Cn. What is that? Very simple. You take any molecule and rotate 360 degree. It's very simple to understand this axis of symmetry. Take any molecule, rotate to 360 degree. When we are rotating 360 degree, and just see before reaching 360 degree, how many times the molecule is appearing same, is giving the same configuration as original. And just find out at what angle of rotation this is producing the same configuration. Then divide 360 degree by the angle at which it is appearing. We will get some values. That value will be given as, that is, n values. So C indicates axis, n indicates fold, n-fold axis. So in this case, you take an example of carbon dioxide, and if you say this is carbon 1, this is carbon dioxide, oxygen 1, this is oxygen 2. So, and if I am piercing through this center carbon, and if I rotate 180 degree, this oxygen will come here and this oxygen will go there. So, by rotating 180 degree, now I will have an axis of symmetry in the case of carbon dioxide. That means 180 degree. So, divide 360 by 180, I will get the 2 value. In this case, carbon dioxide, N is 2. So, that means the carbon dioxide is having C2 axis. So this is the way we are finding out. I already pointed out. It is very difficult to understand this for higher level. Anyhow, those who are interested students, they can observe. So let me conclude now. I will conclude easiest way. So n value, I have already pointed out how to arrive at n value. So rotate the molecule 360 degree and find out at what angle it is appearing in the original configuration. So that angle, divide that. So this carbon dioxide 360 by 180, so 2. So carbon dioxide is having C2 axis. So my question is, whether carbon dioxide is optically active or not? So it is not optically. How? The idea here it is, if n equal to 1, then it shows the optical activity. If n equal to greater than 1, then it will not show optical. Very, very easy. So if carbon dioxide is having a greater than 2 values, it is not optically active. So according to this axis of symmetry, carbon dioxide is optically inactive. Because this is a simple molecule only, we can imagine the axis of symmetry, we can rotate, and you can imagine. When you go for organic molecule containing that is 20, 30 carbon atoms, very, very difficult. That's why I informed you earlier, it is not possible to understand this level. Anyhow, that's an interesting point of view I am explaining. The last one is alternate axis of symmetry. What is alternate axis of symmetry? Again, as usual, a specific example here, it is the example, what I have given is, it is 1,2 dichloroethene. This is the example given here. 1,2 dichloroethene. So this is the trans isomer. I will come and explain later. This is the trans isomer. I will explain later. So if you take example of 1,2 dichloroethane trans isomer and take reflection mirror image. After taking the mirror image, rotate, that is piercing through this, rotate to 180 degree, then automatically you will get this configuration. What way? This is H, the correspondingly, when I rotate here, this will be H and this will be Cl, the same way this will Cl, this will be H. So this will identical this one. So let me conclude now. What is alternate axis? Usually indicated by Sn, S for alternate axis, N again the angle of rotation. Now, take any molecule take a mirror image. After taking mirror image, construct a model and rotate through any angle of rotation. Then, when you are rotating, you just compare with the original configuration. If it coincides, that particular molecule is said to have alternate axis of symmetry. This again, to imagine is very, very difficult. This is for M.Sc level. So let me conclude now. So I will stop with this stage. That is, to be optically active, that is, to show optical activity, a molecule should produce a non-superimposable mirror image. To produce non-superimposable mirror image, the molecule should have no plane of symmetry, no center of symmetry, no axis of symmetry, or no alternate axis of symmetry. Among the four, I have already pointed out, the first one is the most important. That is, plane of symmetry is most important to be sufficient. So I can stop here. But again, one more important information I want to. So even though I am discussing all these informations, examination point of view, I can even simplify in the next class. So you need not worry about this identification of optical activity. Thank you.